On August 10, 2025, at exactly 15:25, a Ukrainian F-16 took off from a mobile runway carrying two GBU-62 JDAM bombs. Its mission was to strike a heavily fortified underground Russian command post in Karen, where 25 senior officers were gathered. Flying at treetop level, evading S-400 radars, and supported by decoy drones, the jet executed a daring pop-up climb to release its payload with surgical precision. Within seconds, the penetrating warheads collapsed the bunker's gallery system, killing the entire command staff and paralyzing operations across the Karen front. This single strike not only destroyed a headquarters but also exposed the vulnerability of centralized command. Could one aircraft in 20 minutes reshape the balance of a battlefield? Before we begin, don't forget to support us by liking this video and subscribing to the channel so you don't miss any future reports. August 10, 2025. At precisely 15:25, deep beneath the city of Karen, a group of Russian commanders gathered around a reinforced underground table. They reviewed deployment plans with an air of confidence, convinced that the bunker's depth and concrete shielding guaranteed their safety. Above them, however, preparations for a precision strike were already in motion. On a mobile runway not far away, a Ukrainian F-16 fighter was completing final checks, armed with weapons designed to penetrate the very illusion of invulnerability. For months, Ukrainian intelligence had studied this facility. Every antenna cluster, signal relay, and ventilation shaft had been mapped. Supply points were tracked, and entry routes cataloged. Imagery and signal analysis revealed its true nature, a hardened command post coordinating operations across the Karen front. Inside at that moment were 25 senior Russian officers, including a battalion commander, staff chiefs, and logistics planners. None were aware that their communications had betrayed them, and that the Ukrainian Air Force was already set to deliver the decisive blow. The mission was entrusted to a single F-16, stripped of escorts to reduce radar exposure. Only surveillance drones and decoys supported the profile, each synchronized to distract and mislead enemy sensors. At 14:57, pre-takeoff checks concluded. On the fighter's wing stations hung two GBU-62 JDAM bombs, each a 454-kilogram penetrating weapon with a delayed fuse set in the tail. The aircraft also carried a chaff pod beneath the fuselage, AIM-120 missiles for self-defense on its wingtips, an ALR-56M radar warning receiver, and an ALE-50 towed decoy cassette. Two external 370-gallon fuel tanks extended range and safety margins for the demanding flight. Software preparation was equally critical. The mission computer was loaded with WGS-84 coordinates, bomb GPS ENUS guidance data, and toss swing parameters. The pilot briefing emphasized why nap of the Earth flight at 50-60 meters altitude was non-negotiable. At such heights, the curvature of the Earth limits radar line of sight. Even advanced S-300 and S-400 systems cannot reliably detect a target flying so low beyond 25 to 30 kilometers. If the fighter could stay masked until reaching JDAM standoff range, the brief radar illumination window could be defeated through jamming, maneuvering, and decoys. At 15:03, the afterburner roared to life. The jet lifted from the auxiliary runway, retracted gear, and immediately descended into a low-altitude profile. Flying this close to the ground demanded extreme precision. Every gust and vibration forced the flight computer to constantly adjust wing load and thrust. The risk of debris ingestion into the engine compressor was ever present. To mitigate this, the route had been plotted along a clean corridor, charted from satellite imagery to avoid loose soil, vegetation, or man-made clutter. Over the border, surveillance UAVs climbed to altitude, maintaining overwatch. They tracked antenna rotation and service door cycles, confirming activity inside the bunker. Yet intelligence planners knew the most dangerous moment was still ahead. The JDAM bombs required altitude and speed to achieve glide range. That meant the F-16 would eventually have to climb above the radar horizon, exposing itself to Russian tracking and fire. At 15:18, the decoy package activated. Several miniature UAVs broadcasted intermittent signals, cluttering radar tables with low RCS echoes. Others left optical traces, injecting noise into the visual confirmation loop. Their task was not to fool operators indefinitely, but to delay recognition by a handful of seconds, long enough for the strike aircraft to maneuver into position. At exactly 15:21, the F-16's ALR-56M threat receiver gave its first warning, radar illumination from the northeast. The pilot reacted instantly, executing a beam maneuver, flying at a right angle to the radar to complicate Doppler discrimination. The ALQ-131 pod blasted broadband noise into the spectrum. Seconds later, the expected SAM launch warning appeared. The pilot deployed the ALE-50 towed decoy, reduced speed slightly, and widened the turn radius to throw off the missile's lead cone. The missile veered toward the decoy and fizzled harmlessly at range. The first defensive exchange was over. For the Ukrainian pilot, this meant one thing: it was time to commit. The radar operator would reacquire the track, and a second firing solution would be seconds away. At 15:22, the F-16 pitched upward at a 35 to 40 degree angle, climbing rapidly to nearly 2,000 meters. This maneuver was not reckless, it was calculated. The altitude and velocity at bomb separation would maximize standoff glide range for the JDAM ERs, pushing the release point several kilometers backward and reducing exposure time. Each JDAM ER combined a hardened steel warhead with a GPS NES guidance kit and extendable wings. The inertial navigation ensured accuracy even under jamming, while the wings turned the bomb into a glider, allowing it to cover tens of kilometers. The delayed fuse, set to 1.1 seconds, was tailored to the underground target. Instead of detonating on impact, the munition would burrow through concrete and trigger inside the ventilation and gallery systems. The design aimed to collapse chambers through pressure shock, destroy ventilation backbones, and disable power systems. On the surface, only a small hole might appear, but inside, entire corridors would collapse. As the first bomb separated, the INS locked and GPS keys synchronized with the mission computer. A millisecond later, the second followed. Both entered glide, wings deploying to maximize range. The F-16 immediately nosed down, descending back into the 50 to 60 meter altitude band, conserving fuel and masking once again under radar coverage. The egress line was charted and clean. Ukrainian intelligence had timed everything to precision. Satellite imagery was fused with signals analysis to determine meeting schedules. The pod sensor on the fighter confirmed terminal guidance, narrowing the window to mere seconds. Both bombs tracked in at a 40-degree dive toward the bunker's reinforced roof. At 15:27, the first penetrator struck within meters of the main ventilation shaft, detonating deep inside the gallery system. Pressure chambers collapsed instantly. Inside the bunker, the meeting disintegrated in chaos. Among the 25 Russian officers were 2 colonels, staff chiefs, and ammunition planners. The first explosion tore through the central gallery, delivering a shockwave that shredded walls and consoles. Seconds later, the second bomb impacted, collapsing the ground floor. Support columns snapped, electrical systems shorted, and internal walls cracked under load. Corridors were blocked, escape impossible. Within moments, the 3-level underground structure folded inward. All 25 officers were lost. The F-16, meanwhile, was already in egress, 6 seconds after bomb release. Flying nap of the Earth, its radar signature was suppressed by ground clutter. Within 17 minutes, the fighter landed on its mobile strip. Radio silence broke only after touchdown. Pod imagery was transferred to backup systems, confirming target destruction. The jet required no rearming. The mission had been decisive. The immediate operational impact was dramatic. The loss of the Kherson headquarters severed Russian command and control. Forward position planning halted for 8 hours. Artillery fire schedules were delayed. Supply authorizations froze. Engineering tasks stopped mid-progress. Drone flights were suspended pending new orders. Without a command node, Russian units sat inactive, unable to relocate or resupply. This was not merely the destruction of a bunker. It was the paralysis of an entire sector. The shock did not end with rubble. It radiated outward through command cycles and logistics nodes. In the immediate hours after impact, frontline routines dissolved into uncertainty. Forward planning was suspended for 8 hours as units awaited new orders. Artillery barrages queued without target data. Engineering missions stopped where they stood. Drone sorties were grounded while communications teams attempted to reroute frequencies. Without a functioning node to authenticate and deconflict transmission, transport orders froze and relocation decisions stalled. Command fragmentation produced contradictory orders, double tasking of batteries, missed fire windows, and batteries unable to engage because remote arming data never arrived. The disruption was granular and systemic. A single precisely placed internal detonation cascaded into 72 hours of degraded coordination across the sector. Intelligence confirmed the tactical picture within 6 hours. The Olashki record entered into Ukrainian intelligence systems, correlated sensor feeds and imagery. Satellite frames, 14 in total, showed the structural collapse. Analysts matched the blast signature to a JDAM ER profile, penetration trace consistent with wing-assisted glide, a measured fuse timing near 1.1 seconds, and blast depth estimated at 3.2 meters. On the ground, field reports corroborated personnel losses, 25 fatalities, among them 2 colonels, 4 lieutenant colonels, and 3 engineering chiefs. The physical evidence, diameter of the surface aperture, depth of structural failure, and internal fragmentation aligned with the munition's forensic profile. These verifications closed the loop between planning, execution, and assessment. The psychological and doctrinal effects were as significant as the material ones. Within days, Russian headquarters discipline shifted, staff visits to forward nodes decreased, decision-making processes lengthened, and concealment became the dominant posture. Command elements that had once accepted proximate risk now retracted deeper underground or relocated to dispersed, lower signature sites. These changes slowed reaction time and complicated command reach, producing a tactical advantage for Ukrainian forces in the near term. On the Ukrainian side, the strike became a proof of concept, an operational template that demonstrated how mobility, precision munitions, and synchronized EWISR could impose disproportionate effects. The technical after-action drove rapid iteration across multiple dimensions. F-16 mission planning and logistics were adjusted. Mobile basing increased, fuel and rearming lines duplicated, and pod systems received software updates to shorten target-to-release timelines. Mission computer algorithms were refined for faster solution generation. Pilot training emphasized the pop-up release profile, low-altitude egress, and counter-EW contingencies. Ammunition handling saw refinements, delayed fuse sensitivity adjustments, improved heat dispersion characteristics, reduced GPS deviation margins, and enhanced reliability checks for wing deployment sequences. On the EW side, jamming signatures and pod data transfer rates were improved to reduce targeting windows to as low as 1.3 seconds. These measures aim to codify the successful elements of the sortie while hedging against identified vulnerabilities, GNSS degradation, DTM errors, and environmental factors that can defeat a glide munition. Operationally, Kiev's standardized aspects of the sortie model, reliance on mobile runways, minimal ground time at forward strips, and compact mission durations. The specific Karen mission itself lasted only 20 minutes from takeoff to landing, the jet returning to the mobile strip within 17 minutes. In practice, the mission combined multiple weapons and sensor nodes. 2 JDAM penetrators achieved the collapse, but subsequent doctrine emphasized single munition, short-duration sorties where appropriate to preserve ambiguity and reduce exposure. Pod imagery was pushed to redundant storage immediately after egress. Radio silence remained until secure landing and confirmation, limiting opportunities for post-strike geo-tracking. The result was an operational profile that traded permanence for unpredictability, rapid high-precision strikes that were difficult to attribute in real time and even harder to intercept after the fact. But the method exposed inherent limitations and failure modes: deep shelters with redundant ventilation, multiple shafts, off-grid power, and hardened fiber runs can blunt the effect of a pair of penetrating detonations. Environmental conditions, wind, weak GNSS signals, incorrect digital terrain models, or a failure in wing deployment can cause the glide package to miss or detonate ineffective shallow strikes. The planners acknowledged that success depended on a chain of functions: accurate ISR to confirm target occupancy, precise DTM and GPS INS data, reliable decoys and jammers to cover the pop-up, and intact tracking UAVs to provide terminal confirmation. Any break in that chain produced failure. Thus, the attack's success was simultaneously an operational triumph and a warning. Tactical advantage can be fleeting. Defenders will adapt. From the defender's perspective, mitigation options were straightforward but costly. Move command deeper, add more ventilation and redundant power routes, increase the density of close-in air defense, and harden access points. Every enhancement, however, creates new physical or operational weak points. Ventilation and power must surface somewhere. Antennas must be emplaced. Fiber or radio links must terminate. Each of these is a potential signature for persistent ISR. The attacker exploits geometry and timing, the confluence of an exposed vector with a narrow window of presence, to collapse a command node with surgical economy. The Karen strike illustrated an enduring principle of asymmetric air-land operations. Precision, timely intelligence, and tactical mobility can produce strategic effect with limited means. The strike severed a battalion's decision and supply node at midday, paralyzing a front and creating a window for follow-on pressure on 8 axes. The absence of immediate Russian counteraction, backup personnel were not ready, the secondary headquarters was remote, and data transfer had to be done manually, meant Ukraine could press operational advantage in the immediate 72-hour window. That vacuum of command and the resulting disorder at the tactical level translated into measurable gains on multiple fronts. Yet the account must end with the same caution displayed by the planners before launch. What works today may not work tomorrow. The system's fragility is shared. Success depends on meticulous synchronization across intelligence, EW, flight operations, and ordnance reliability. The defenders will adapt to observed patterns. The attacker must diversify routes, redundant sensors, and contingency measures. Still, on August 10, 2025 at 15:27, a calculated combination of stealth by altitude, synchronized decoys, EW suppression, and precision-penetrating munitions collapsed a clandestine command node and imposed disproportionate operational effects. The mission's precision and the subsequent doctrinal changes underscore how modern conflict rewards integration of tech and tradecraft. The tactical result was decisive. The strategic implications will reverberate as both sides reassess posture, protection, and the costs of centralized command in a contested battle space. The ripple of effects from Karen continued beyond immediate command paralysis into doctrine, procurement, and the psychology of command. Intelligence and operations staffs on both sides treated the strike as a case study, how a single, well-timed penetration can collapse not only concrete and circuitry, but an entire decision cycle. For the attacker, the strike validated investment in integrated ISR-to-shooter chains and the tactical use of low-signature basing. For the defender, it exposed the unavoidable trade-offs of depth versus connectivity. The explosion that detonated within the gallery system was configured deliberately to exploit that trade-off: time to collapse ventilation, compress internal air volumes, and bring ceilings down upon personnel and equipment, producing maximum internal disruption while leaving a relatively modest surface aperture. That technical choice shaped the operational consequences. Reconstruction of the event showed how the combination of GPS-INS guidance, wing-assisted standoff, and a delayed 1.1-second fuse produced subsurface detonation at roughly 3.2 meters depth, maximizing underground pressure effects rather than surface blast. The forensic profile diameter of the crater, depth of collapse, and internal fragmentation matched the JDAM employment profile in imagery and field reports, confirming both weapon selection and firing parameters. The human cost, corroborated by multiple field reports and satellite frames, was the loss of 25 officers, including senior tactical and engineering leaders. Those personnel losses were the proximate cause of the immediate command vacuum. Doctrinally, the strike forced a reassessment of centralized command in contested space. Where previously a forward-located headquarters offered speed of decision and proximate situational awareness, the Karen case demonstrated how physical concentration of decision-makers can be a vulnerability when persistent ISR and precision-penetrating munitions are in play. The defenders' immediate mitigations were predictable: deeper and more redundant sheltering, dispersed C2 nodes, and expanded close-in defenses, but each measure imposes cost and creates secondary signatures. Ventilation shafts, power conduits, and communications terminations must reach the surface. Hardening those interfaces drives expense and complexity, and crucially, lengthens the time required for staff to reconstitute a functioning battle rhythm after a strike. From the attacker's perspective, the mission crystallized a set of operational precepts that can be replicated but not assumed to be inertial. Mobility of basing, compressed time on ground, rapid sensor-to-shooter loops, and refined EW decoy packages were codified into new standard operating procedures. The F-16 sortie, short, surgical, and built around minimal exposure, became a doctrinal exemplar: mobile runway launch, a 20-minute mission clock, immediate egress, and secure data exfiltration of pod imagery. Redundancies were layered: duplicated fuel lines for dispersed strips, faster pod data pipelines into redundant storage, and algorithmic tweaks to mission computers to reduce target-to-release timelines to near 1-second ranges where possible. These changes increased sortie tempo and reduced predictable windows for defensive reacquisition, yet the planners who wrote the after-action acknowledged the fragility of success. Environmental variability, unexpected wind shear during the glide phase, GNSS degradation, or an erroneous digital terrain model could scatter an otherwise tightly choreographed shot. A failed wing deployment or a jammed fuse would convert a tactical advantage into a missed opportunity, or worse, collateral damage. Consequently, operational doctrine incorporated contingency sets, alternate strike axes, multiple ISR threads to confirm occupancy, cross-queued sensor pods to maintain terminal lock, and pre-planned egress corridors that accounted for multiple SAM engagement scenarios. The attack's reliability depended on chain integrity. Break any single link, and the product of the equation collapses. Psychologically, the effects were immediate and measurable. Units that had previously relied on rapid forward-located guidance now delayed movements. Officers reduced visits to forward nodes and increased reliance on pre-authorized lower-velocity decision mechanisms. For the attacker, this amounted to a temporary expansion of the operational neighborhood, a 72-hour window in which the defender's capacity to coordinate and concentrate fires was noticeably degraded. Kiev's advantage was not merely the physical void left by the collapsed headquarters, but the temporal shock that exposed seams across 8 axes of pressure. The strike also reframed how precision munitions are employed against hardened subterranean targets, where bunker busting traditionally emphasized large penetrator mass and multiple sequential strikes to create collapse. The use of wing standoff kits with precise delayed fusing offered a different economy: fewer munitions, shorter aircraft exposure, and the potential to collapse internal systems without massive surface signatures. This economy of effect, however, relies on superior ISR and synchronization, an expensive but repeatable investment for an air force that can field it. Defenders therefore face the stark choice of investing in extensive hardening at high cost or accepting increased risk to forward-located decision nodes. Closing the account, the Karen mission is a lesson in integration. Weapons without ISR are blind. ISR without precision weapons is impotent. Mobility without hardened procedures is vulnerable. The successful sortie reduced a battalion's nerve center to rubble, disrupted operations for days, and forced adaptation at multiple levels of command and procurement. Yet it also underlined a simple truth of modern conflict: tactical ingenuity and systems integration yield outsized effects, but those effects are perishable as adversaries observe, learn, and harden. The operation's tactical precision and immediate strategic impact were beyond doubt. The long-term balance will depend on which side adapts more quickly, who can afford the required hardening, and who can sustain the ISR-to-shooter cadence under pressure. On balance, August 10th's penetration at 1527 stands as a calibrated demonstration of contemporary asymmetric air-land effects. Small assets, coordinated through high-quality intelligence and executed with disciplined tactics, can impose strategic dilemmas far exceeding their physical footprint. The report concludes not with triumphalism but with the acknowledgement that warfare remains an iterative contest. Today's method provokes tomorrow's countermeasure, and the next successful strike will be the one that learns from both.